Welcome again to our virtual lecture. This is part P of chapter 3, molecules and compound. There are just few sections I would like to go through before we wrap up chapter 3. Allow me to share my screen. As usual, I'll be making some notes, working some worked example. You should have a pen, a paper, so that you take notes, you make your own notes. Today, this is the roadmap of what I intend to cover in section 3.6. All right, section 3.6, we will look at the molecular compounds and formulas and names. We will look at the criteria by which we name the molecular compounds. The summary of inorganic compounds, formula mass, how to find the molar mass of a compounds given the periodic table, the mole concept and compounds, and we will also look at the compounds, determining the empirical formula. And lastly, in section 3.11, organic compounds. So let's see in part 3.6, molecular compounds. You say molecular compounds, these are compounds which are made up of two non-metals, unlike ionic compounds. Remember, ionic compounds are compounds made up of a metal and a non-metal, or a metal and a polyatomic ion. Molecular compounds, you cannot determine its formula easily using the crossover rule we talked about, but it's a different ball game here. For example, here are just few examples of molecular compounds. You cannot readily determine their constituent element because of the same combination element may form many different compounds like nitrogen and oxygen. There is nitrogen monoxide, nitrogen dioxide, dinitrogen monoxide, dinitrogen trioxide, dinitrogen tetroxide, and so forth. You cannot easily use the crossover rule. So molecular compounds, when we say molecular compounds, these consist of two or more non-metals. Let's just minimize this, and we'll see how the non-metal ionic, remember what we say, ionic compounds versus molecular. This is metal plus non-metal. This is what we looked at in the last section. Here is non-metal plus non-metal. We have two non-metals in ionic compound. So when we talk about that, you need to know what makes up the molecular compound. Let's see, in terms of what makes up those, you need to know that there are two or more non-metals. Generally, you write the name of the element with the smallest group number name. So if you look at the, you start with the smallest group number. What does this mean? In case of oxygen and carbon, writing the one with the closest, this is group 4 and this is group 6. So we start with either carbon monoxide, carbon dioxide. If you look at the nitrogen and oxygen, this is group 5A, and this is group 6. This is group 6A. So we say 6A, group 6A. All right, group 5A, group 6A. So we start with the lowest number, NO, NO, or NO2. That's what this bullet point means, that we generally write the element with the smallest group number. That's the criteria for writing the correct chemical formula for molecular compounds. If two elements lie in the same group, then write the element with the greatest row number. Oxygen and sulfur, for example. This is in sulfur is in row 3. This is row 2. So this is row 2. This is row 3 or period 3. This is period 2 on the periodic table. So when we have that, we'll have to write the one with the greatest period number. So if I'm to write sulfur dioxide, we start with SO2. This is sulfur dioxide, or SO3, because of the one they all lie in group 6. This is put in group what? Group 16 or 6A. Or 6A is the same thing. They lie on the same row. So the one with the greatest row number is written first. The one below is written because row 1, row 2, row 3 in writing the correct formula for molecular compounds. On the slide you see here, this is just summarize the criteria by which you write the correct formula for what? For molecular compound. Please do not confuse with the crossover rule. Crossover rule is for ionic compound, but this slide right here just summarizes how to write the correct formula for molecular compound. In naming them, you need to learn here naming molecular compounds. You need to learn the prefixes. What are these prefixes? Prefixes here indicate how many elements you have or how many atoms you have for a particular element in a compound. And we learned this before. It's just a continuation of the prefixes we looked at in naming the hydrates. So here's the prefix, which indicate how many they are. I'm just going to show you momentarily those prefixes. And then the first element, the second element, and the base element. For example, here, I can say this is 2O4. This is called dinitrogen. This is nitrogen tetroxide, or sometimes it could be tetroxide. All right, some others call this dinitrogen tetroxide for the oxide. You notice that I've used the prefix here, di. This is where we have the prefix di. This is tetra for 4, and this is di for 2. The prefix here is used to indicate how many they are. And then the element, name of the first element, nitrogen, this is the first element. And then the prefix for the second one, this is the prefix, tetra for 4, and then the base element, and you add the IDE. You see this IDE, for most part, there is an IDE for naming that. So here, the prefixes are the same as those used in naming the hydrates. That's what I just mentioned, that we use the prefixes, and here they are. Please use index card to learn until you commit to your memory. Mono means one, all right? For example, here, how we use mono is C, O, this is carbon, and then mono, you drop the O and then you say monoxide like that. It's not mono, it's not monoxide. All right. You drop the file. If you have that, you drop the monoxide when you have only one. Whereas CO2, you use the carbon di, and then oxide like that, carbon dioxide. There's the prefix here, which indicate how many we have, how many oxygen. So the di is used for 2, tri for 3, tetra for 4, penta for 5, hexa for 6, hepta for 7, octa, nona, and deca. You need to learn this. You see, I will not give you an exam. You need to remember that we use deca, penta, hepta, and so forth. This is what you will be using, unlike the criteria by using the crossover. Do not think that we use the crossover. If there is only one atom of the first element in natural in the formula, the prefix mono is normally omitted. What does that mean? We do not say monocarbon or monocarbon and then dioxide. Please take note of when to use mono. When to use mono. Here is a learning checker, which word indicates that two water molecules are associated with a substance in a chemical compound. I think this is going back to a previous section on naming the hydrates, because it's talking about the water molecule associated with a compound, which has nothing to do with the molecular compound. This slide here was meant for the hydrates. Just take note of that. But nevertheless, it's the same prefix. We use di. That means we have two water molecules. This is a conceptual question on section 3.8 or conceptual problem number 3.8. The compound CnCl, those are two nonmetals, is nitrogen trichloride. Look at the word tri, which means we have 3 chlorine, but AlCl is aluminum chloride. This is because you have to distinguish between molecular compound. This is a molecular compound, whereas this one is an ionic compound. The challenge here is, all right, the challenge here is failing to classify a compound as molecular compound or ionic compound. This is a metal, this is a non-metal, it's ionic, whereas this is a non-metal, this is a non-metal. You need to know that. If you did not master the periodic table, breaking it into metals, non-metals, and metalloids, when you are presented with such problems, it will be very difficult to draw a conclusion for the problem. So here, the correct answer is B. The name forms different because NCl3 is molecular compound. That's correct. And AlCl3 is an ionic compound. Prefixes such as mono, di, tri, etc. are used for molecular compound, but not for ionic compound. Common mistake I see student is using the prefixes, where they shouldn't be. So the point here is knowing the difference between ionic and molecular compound. Let's shift gears to acids. And acids, we have two types of acids. All right. These are this is aqueous solution. It's an aqueous solution, which means AQ, all right, is means dissolved in what? Dissolved in H2O or dissolved in water. So general molecular compounds that releases hydrogen when dissolved in water are called acid. There are three definitions of an acid, all right? Three definition. I'm just gonna draw a parallel between acid that we have here. There is Arrhenius, there is Bronsted, Lowry, and then there is the Lewis definition. You have to know the definition of an acid according to Arrhenius. Here is, you define this as any substance that hydrogen ion, you must say hydrogen ion in H2O when dissolved in water. And I think this is the definition of Arrhenius. But Bronsted Lowry definition is simply proton donor. It donates proton. And here is electron pair it accept 2 electrons or even more than that. Sometimes you may be asked, what is the definition of a Bronsted acid? What's the definition of the Lewis electron pair acceptor? According to Lewis, according to Arrhenius, you need to know what they are. As opposed to the base, let me just define for you according to Arrhenius, Bronsted, Lowry, and according to Lewis. So you should know the definition of Arrhenius according to, the definition of a base according to Arrhenius, base according to Bronsted, and base according to Lewis. Here is you can say anything that produce OH. This is hydroxide, by the way. See, hydroxide ion in H2O when dissolved in water, it produces hydroxide ion. The key thing here is hydroxide. And according to Bronsted, this is just proton acceptor. It accepts the proton. The acid donate base accept. And according to Lewis, this is electron pair donor. It donates a pair of electrons, a pair of 2 dots. You'll see that later. So I've just defined an acid according to Bronsted, Lowry, according to Arrhenius, and according to Lewis. So there are 3 definitions for that. Acids are composed of hydrogen, usually written first in the formulas, and one of the more non-metals written second. It's just the properties of an acid. Please take note of this. Acid generally taste sour, whereas bases taste bitter. Dissolved in metals, all right, dissolved many metals such as zinc. So given this, there will be an experiment on a single replacement reaction in the lab. you will see the reaction between some acid with the metals. So they react with metals in single replacement reaction. Generally, the formula start with H. It's just HCl is a molecular compound that, when dissolved in water, produces hydrogen ion. Take note of aqueous. Aqueous means dissolved in H2O. There are two categories of acids: binary acid and oxyacids. Binary acids are composed of hydrogen and a non-metal. From the word pi, pi means two, so it has pi means this an hydrogen and a non-metal, and a nitrogen and a non-metal. Oxyacid here, oxyacid is polyatomic polyatomic ion, all right? It has three things: hydrogen, oxygen, and must be aqueous. Whereas pi is just hydrogen, aqueous, all right, and a non-metal. You got to see how you distinguish between the two here. Hydrogen is the criteria by which you can classify the binary acids, whereas the oxyacid, they have oxygen, all right? They have oxygen, aqueous, and hydrogen. There's a systematic way of naming them. Or oxyacids, they have oxyanion. Oxyanion is polyatomic ion, contain polyatomic ion. We'll see that how we write that. Naming of binary acids, that means they have two elements, a metal and a non-metal. We use the word hydro, and then we change the ending to ICE, following with a non-metal base name. Write the word acid at the end. So you must write the word at the end. So for binary, you see this is HCl, this is hydro. Look at how we write that: hydrochloric, and then the word acid. What is mentioned here is the word hydro. You see this hydro, and followed by the base name. Base name is chlor. You see this, what's meant by chloroform. Non-metal base name. Non-metals here is chlorine. We have chloro. And then we add the ICE. Instead of chlorine, you write the IC here, IC, following the non-metal base ICE. Write the word acid at the end of the write the word acid at the end. So that's what I do have here. So when we look at compound, and must be aqueous, by the way, aqueous like that, this is hydro, and by the way, you should use correct spelling. Hydrofluoric acid, HI, and then aqueous. This is hydroiodic acid, hydroiodic acid, PR, aqueous. This is hydrochromic acid. See how you write hydroiodic, hydrofluoric, okay, hydrochromic, and so forth. We use hydro for binary. These are binary acid. Hydro base, I've just given you, that's the criteria for naming that. Which of the following is the formula for hydrochloric acid? I just gave you that. Is correct answer is C. The correct answer is C for that. Correct answer for that is C. You can be given the chemical name and you are asked to write the formula. What is the chemical formula for hydrofluoric acids. Correct answer is A for that. The correct answer for this is A. This is hydrochloric acid. This is hydrobromic acid. This is hydroiodic acid. Please learn those. Use 4x6 index card, whichever way is convenient for you in learning them. Please have, 1 page of binary acid. And the only 2 areas you will be tested on that is when given the chemical formula, are you able to name, or when you are given the chemical name, are you able to write the correct chemical formula for that acid? That's binary acid. And please, we use hydro for only binary. When you see oxy acids, naming of oxy acid, here oxy acids contain here oxy acid, one hydrogen, two oxygen, and three it must be another non-metal. You can say that polyatomic. You can just simply say polyatomic. Polyatomic ion. So that's how I look at the oxy acid. If polyatomic ion, you see this polyatomic ions end with ATE chain and the IC. For this to illustrate, you'll be given such as H and O2 and H here H and O3. This one has, if you look at the naming of polyatomic ion, N2 negative, and this is negative. We name this as nitrate, nitrite, ITE. Please go back to polyatomic ion so that you are able to handle the oxy acids from the polyatomic ion. Gotta go back to the basic. This is nitrate. Nitrate, it's ending ATE. This bullet point here indicates that if polyatomic ions end in ATE, change the ending to ICE. It's just gonna take a while or a couple of studying to really understand how ITE and ATE works from polyatomic ions. So how do we change to ICE? If I go back here, and this is aqueous, this is aqueous, we say this is nitrous, OUS. Look at this. And this one is nitric. Look at how I've changed from ATE here. Look at the ATE and ATE. ITE, ITE, and AT is mentioned here. If polyatomic ions end with ITE, you change the ending to OUS. So you have to go back again. If you have something like this, no, 3, I'll use 3 here with the 3 negative, and EO4 with the 3 negative. This is phosphide. You need to learn them. And this is phosphate, ATE, phosphate, phosphate. How you name the acid will determine on polyatomic ion. We have also sightings as SO3 to negative, SO4 to negative. This is sulfide, ITE, and this is sulfate, ATE. How we use this polyatomic ion in so anion will determine the name. with the word acid at the end. For either of these, you have to add acid at the end of acid. Oxyanion ending with ATE, the base name of oxyanion, and then the word ICE. I gave you an example here of nitric and nitrous acid. And by the way, this is acid right here. And then the word acid, nitrous acid, nitric acid, nitrous acid, nitric acid. Oxyanion ending with ATE, we end with OUS. You see, this is because we have the polyatomic ion ITE, nitrous. So this will be nitrous acid. It follows also with the rest, okay? Polyatomic ion. So let's see, practice. I know you have the slide for this. This is the correct naming for just an example, assuming that you have learned naming of oxyanion and binary acids, hydrosulfuric acid, acetic acid, just few of those common acids given. I will highly recommend that you go learn the polyatomic ions so that when you are given in as an oxyanion or as an anion in oxyacids, you'll be able to name the acid appropriately. Let's see, writing the formulas for acid. When the name ends, write the name. When the name ends in acid, the formula starts with H followed by the anion. Write the formula as if it is ionic, even though it is molecular. So that's just how we write the correct formula. Hydro prefix we use for that. I gave you earlier on how we change the ending ATE, ITE to IC, OUS, and so forth. Learn how those happen. This is just tagging the aspirin, acid rain. You can read more in the text about the acid rain and what causes acid rain. 3.7, this is just a summary of naming inorganic compound. Inorganic compound are those compounds derived from metals as opposed to organic compounds, which we look at in section 3.11. There is a whole course, or there are courses for compounds that are derived from the element carbon. Okay, we call it organic compounds and hydrogen, so forth. Let's shift gears to 3.8. 3.8, formula mass and the mole concept for compound. What do we mean by formula mass? The mass of an individual molecule or formula unit. Remember, molecule is the simplest form of molecular compound, but the simplest form of ionic compound is formula unit, but they mean the same things when determining the molecular mass or molecular weight. Molecular weight for formula for ionic compound, molecular mass for molecular compound or covalent, sometimes it's covalent compound. How do you find the molecular mass? E.g., for example, molar mass of H2O, for example, like that. This bullet point number 2, sum of the masses of atomic mass of single molecule or formula will equal sum of parts, all right? Yes, so here you say hydrogen is 1.01. This is from the periodic table. This number here is from the periodic table. Times, all right? Times 2 equals 2.02. Oxygen equals to 1 times, I'm just going to approximate that to 16, 0. We write 18.02 grams, 0.02 grams. And when you have that, all right, when you have that, it means you have only one, all right? Not, this is AMU, by the way. When you say atomic mass unit, AMU, AMU, this stands for atomic mass unit, and this is a unit used by chemists, all right, to represent the mass of one atom. So to give you an idea of what an AMU stands for, it's 1.67 times 10 raised to negative 24 grams. Maybe you can relate to this since you have used in the lab, or you know what a gram is. 1 or 23 zeros. So this is like a small value, 23 zeros before you write this number, 0.67, and we use our AMU here, which means if I have the ability to take one oxygen atom and two oxygen atom, it will weigh this. If you want to change to grams, of course, you use the conversion factor here. Quite often you may see the molar mass. See this molar mass. That means if you have 1 mole of formula unit, that means 1 mole of formula, 1 mole of what molecule. That means Avogadro number. If I have a Avogadro number of H2O, it will weigh 18.02 grams per mole. That's the molar mass, so that you can relate this. This is only 1 oxygen and 2 hydrogen atoms. We talk about it's the same numerical value, but we use AMU for atomic mass unit. But if we have Avogadro number of these units, Avogadro water molecule, we talk about grams per mole. That means you can physically see 18.02 grams. So you go in the lab, weigh out 18.02 grams of H2O. That means you have Avogadro water molecules, So when you do that, please remember there's a difference between molar mass and molar mass and atomic mass. Atomic mass is in AMU, molar mass in grams per mole. Let's see, the molar mass of an element is equals to atomic mass. Yes, molar mass. This is the molar mass of water molecule, which is equivalent to atomic mass. Atomic mass is in AMU, atomic mass in AMU. So this is A atomic number. No, this is the position on the periodic table. We haven't talked about oxidation number and the valence electron. It will come back towards the end of the semester. You should know all those key terms. So molar mass of a compound, I just explained that. Here I can say 1 mole equals 6.02 times 10 raised to 23 equals to molar mass. From this, we can have different conversion factors to convert from one unit to another unit. So molar mass of a compound, the mass in grams of 1 mole of a molecule or formula units. It is numerically equivalent to formula mass, except that the units are in grams per mole. So if you look at here, 1 mole of H2O, that means it contains Avogadro number of water molecules. 1 mole here contains Avogadro water molecules, has the same numerical value as its atomic mass, except that the unit is grams per mole, grams per mole. And it is pretty straightforward. Given the periodic table, you can find the molar mass of any compound. Any compound, given the periodic table, you should be able to find the molar mass. And remember, always use the correct units. Molar mass is expressed in grams per mole, in grams per mole. This is just an equivalent statement we can use to convert between molecules and mass, and here is just the conversion factor. Depending on where you want to cancel, you can cancel this using the CO2 as an example. We can convert between molecules or grams of any compound, not necessarily CO2. Uh, it will take practice for you to understand how to convert between molecules, moles, and grams of A from the periodic table. So here is an example of a problem where you will be required to use dimensional analysis. Here, use dimensional analysis. And the question here is how many molecules? This is not moles though. How many molecules of methane, this is methane CH4, are in 48.2 grams of this compound? At the outset, you need to understand that 1 mole of C4 contains Avogadro number, which is 6.02 times 10 raised to 23 molecules of CH4, which is equals to molar mass. And the molar mass of this is, all right, the molar mass of this is 16.04 grams per mole. This is the molar mass of methane, CH4. So this question is about the molecules. So here is the molecules and grams. So we'll have to derive our equivalent statement from here. Not moles. We're not talking about the moles, it's the molecule. So how are you going to set up? This is how you set up. (48.2 grams of CH4). All right, 6.022 times 10 raised to 23 over 16.04 grams of CH4. We cancel that, on your calculator. You should get something 1.81 times 10 raised to 24 molecules. The unit here is molecules. So the correct answer for that is C. Just plug in your calculator. Take note of molecules. We just use that. Practice on converting between molecules to grams and grams to molecules, or moles to grams and grams to moles, and either molecules to grams and so forth, using the equivalent statement you need to understand. Previously, we were only looking at one element, but here we have to use the periodic table if not given. If we are given, you have to, if you are not given, you have to use the periodic table. Sometimes you'll be given. And by the way, how I ended up with 16 is using the periodic table. 1 carbons weigh 12. By the way, molar mass of CH4 given by C equals 12 1 plus hydrogen is 1 times 1.01, right? This is, we have 4, so it's going to be 4.04. So that's how to find the molar mass. In case you're wondering how did I end up with 16 here, use the periodic table. Sometimes you may be given for that. You may be given for that. So learn more, go back and do more practice on that. Second, we have 2 more sections. 9.3, composition of a compound, a chemical formula in combination with molar masses of its constituent element indicates the relative quantities of each one of them. In this section, you will be asked to find the mass percent of a compound, which is the mass of each. You need to know the formula for the compound, the experimental mass analysis of the compound, and then you find it as percent. This is a equation you learn, you'll see in the lab as well. You'll be required to determine the mass percent of element X. This is just a bullet point. How to find the mass percent of an element. It's the mass of times number of mass of element X in 1 mole of a compound over the molar mass of 1 mole of a compound times 100. For example, here, we have to know which one, without doing any calculation, list the element in C6H6O in order of decreasing mass percent decreasing. This way is more, we have 6. This way, the least, so it's gonna be the last one. If you use elimination method, C and D are wrong. We are left with this, carbon, oxygen. Even though carbon weighs more compared to oxygen, look at the relative number. We have 6, yet we have 1 here. So the correct answer is A for that. Correct answer is A. Well, calculate the mass percent of nitrogen in the following compound. How will you calculate the mass percent of in the compound? Given the periodic table, you need to find the atomic mass of platinum, 2 chlorines, 2 times 1 nitrogen, 2 times 3 hydrogens. You add up everything, and here, molar mass of PtCl2 is 301. To say per mole. This is the molar mass of the compound. Now, mass percent of nitrogen is given by the mass of nitrogen over molar mass times 100%. Times 100%. Look at, we are looking at nitrogen, and it's not only nitrogen. Here, there is 2 times 1, so we have 2 nitrogens. So it's going to be 14.01 times 2 over 301.10 grams should be 9.34, which is B in this case. It'll be, please try with your calculator. We have 2 nitrogens. Look at how I'm multiplying 2 times 1. Don't forget to multiply by 2. If it was chlorine, it is going to be times 2. If it was nitrogen, 2 times, hydrogen, 2 times 3, 6 hydrogens times the atomic mass of hydrogen. If it was platinum, it's going to be the atomic mass of platinum at the top over the molar mass times 100. Sometimes maybe if you add all of them because of the rounding off of the atomic masses on the periodic table, the total should add up to 100. So correct answer for that is B. Mass percent is a conversion. You can look at how conversion factor can be used. In this case, how you interpret the chemical formula for H2O, the ratio is based on the number of moles. So you read this that for every 2 moles of hydrogen, you have 1 mole of H2O, not ml, not grams. Correct answer is C for this. Let's see the empirical formula. You should be able to define this. Empirical formula is simply the simplest whole number ratio of atoms of an element in a compound. Not a ratio of masses, but ratio of moles. In a compound, they can be determined from 1, mass percent, can be given in mass percent, or masses of each element formed when a compound is given. This is from the decomposition. By the way, we'll look at how to use decomposition of hydrocarbon to find the empirical formula. So if you are given the percentages, assume they are just grams. In other words, for example, if it is 46.02% carbon, this is the same as 46.02 grams of carbon. You just assume that you have, whatever percent you are given, convert the percentages to grams. It's just assuming. Technically, there is no calculation. Whatever you see the numerical value for percent, that is just the numerical value for grams and so on. Assume you have 100 grams of the compound, always assume. So if you are given, if there are only 2 elements in a compound, you are given the percent of 1, assume, you have 100, you subtract the percent of the other one to get the mass of the second element. If already given in grams, then you don't need to do anything, just use the grams given as it is. Then you convert the mole, grams to moles using the molar mass of each element. Of course, you gotta use the periodic table. You use the periodic table for that. And then see the formula using the calculated moles, and then you do that. Now, sometimes you may have to really pay attention to your calculation, divide, or, by the way, point number 4, you should be able to list. I will not, or no one will ask you to list them all, but are you able to apply problem in order to calculate the empirical formula? So you divide by what? Divide all number of moles across by the simplest number of moles. If the result is within 0.1 of a whole number rounded up to a whole number, you got to be careful with this. If the subscripts are not whole numbers, multiply all mole ratio by a number to make it a whole number. This is where you need to learn what number should I multiply by to make it a whole number. Let's say, for example, I have here mg, or like that, and I have here 1.1, and then here 1.5. I have to look at the multiple here to make our number is 2, multiply across by 2, and then I'll just make it, I just made up this. So it's going to be mg 2.2, and then 3, like that. So you round up of these to mg Even though we don't have this, by the way, I'm just going to show you, how you multiply by 0.2 here. 1.5, don't round it off. You have to pick a number which will multiply by it. If the ratio is 0.5, you multiply by 2. This is where we have 0.5. Not the whole thing is 0.5, but if you have 0.5, you multiply by 2.33 or 0.67. Let's say you have 1.67 or 2.67 and so forth. You will have to multiply by 3, all right, multiply by 3 and so forth. So you have to know when to multiply by what number. And maybe here is an example on how to calculate, all right, how to calculate the percent of empirical formula. Let's see, what is the empirical formula for a compound containing 3.8 3.80 3.8 grams of carbon, 16.2 grams of hydrogen, 45.1 grams of nitrogen. So here, if you add all the percentages, should give you 100. So I just have to draw a parallel here, depending on how you look at it. Empirical formula, we have carbon, we have hydrogen, we have nitrogen. So to start off with, you say mass in grams. Mass in grams. So assume the percent to be grams. So this is 38.8 grams. This is 16.2 grams, and this is 45.1 grams. So we have used here, look at what I'm doing. I'm changing or converting, assuming that we have grams. So here, number of moles. The number of moles is the number of moles. You divide by the atomic mass, 38.8 over 12.01, 16.2 over 1.01, and 45.1 over 14.01. These are just atomic masses of each one of them. I'm converting it to number of moles. Converting to number of moles, this will give me here, it will be 3. If you use a different color, this will be 3.23 is if I divide by the smallest here, divide by smallest, here should be smallest. Okay, it's 2, it's 2, the smallest is 2. So here 2, 3.22, and here 3.22 over 3.22, the smallest. So doesn't really matter which one you are using, so long as it's smallest. So here and here, this will be 1, here and here, this will be 4.98, 4.98, and here 1. It's just like 1. So if I look at this, it's going to be mole ratio here. 1, 5, 1. And the empirical formula is CH5N. CH5N, and this is the empirical formula for that. CH5 and CH5 N. Okay. So that's how you will proceed. Please remember how I started. Okay, you can have your own way of, learning how to determine the empirical formula for masses. If you are given the masses, you don't have to worry about that. So I'll do the same thing for this. If you want to subtract from nitrogen, the correct answer for this is try that. The correct answer for this is N O to please try this question on your own. You should get this as a learning, as a practice. Even for this, you should get for arsenic AS 2 or 3 like that. You should be able to get this for this question. Please schedule a Zoom meeting if you get stuck, or use SI support to see if you can if you get stuck before you come back to me. All right. So having gone through the empirical formula, you may do more end of chapter problem as a practice. Even on Alex, you should be able to get it right, the determination of the empirical formula for compound. Now, molecular compounds shows the actual number. Molecular compound is a whole multiple of empirical formula. So let me abbreviate this as molecular formula is given by empirical formula times n, where n get to be a whole number. N is given by the molecular and this is always given, by the way, always given over, let's say this is empirical formula right here. This is the basically molar mass of empirical formula. Molar mass of empirical formula. All right. Use the periodic table here. All right. Use periodic table. If you are not given, make sure you use the periodic table, so that here the molar mass is always given, or molecular formula, molar mass always given. You'll be given that at the top, and then the empirical formula mass is just the molar mass of empirical formula. Use the periodic table for that. In order to get the what? In order to get the n, and you don't leave it this way, you got to open the parentheses. Probably once you get in there, we'll see how to proceed with that. Let's say if we are asked to find the empirical formula for a compound, or a known compound is found to contain 40% carbon, 6.7 hydrogen, and 53.3 oxygen with a molecular mass of 60. What is the molecular formula for that compound? Molecular formula, we need to proceed this way. First, we need to find you need to find the empirical formula. We have carbon, we have hydrogen, and we have oxygen. Yes, we have oxygen. Remember what I say, you have to assume that you have grams here. So this will be 40, all right, grams. We have 40.0 and 6.7 grams, 53.3 grams. Remember, you have grams. This is the mass. This is the mass. Moles is 40.0 over 12.01. Remember, these are grams. Atomic mass is 6.7 over 1.01. This atomic mass of hydrogen, and oxygen 53.3 grams over 16.00. This atomic mass for oxygen. Let's see each one of them. This will give you 3.3, 3, 6.6, 0.03, and 3.33. So that if we divide by the smallest, 3.336. So now empirical formula is CH4, and this is 2. This is the empirical formula. And then empirical formula mass, this is the molar mass of empirical formula, is given by C is 12.01, hydrogen is 1.01 times 2, and oxygen is 16.00 times 1. This will be 30.03 grams per mole, This is the empirical formula. From the periodic table, this is from periodic table, all right? Periodic table. So when I have that, it's gonna be just periodic table. And what I do here is N, therefore, N equals to molar mass of empirical formula mass, which will be what? 60 point, no, this is 60.0 grams per mole. It's given here. See this? This is why we are given the molar mass of 30.03 grams per mole. So that this will cancel out. This will cancel out. All right. And this will be 2. Therefore, molecular formula is given by empirical formula times 2, which is CH2O 2. It will be C2H4O2. And here is the correct answer for that. That's the correct answer. What I've used here, or what I've illustrated, is how to determine the molecular formula given the percent composition of a known compound, given the position of a known compound. Sometimes, composition, sometimes you may be given the empirical formula and you don't have to worry about, starting from scratch to determine the empirical formula. Some problems might be part A is find the empirical formula, part B is find the molecular formula. It's the same thing, or you have to go all 9 yards starting from the empirical formula first, and then you go all the way to molecular formula, all the way to molecular formula. Well, shifting gears to combustion, combustion is just burning compound is to burn a known mass of the compound and weighing the compounds of the product. This is combustion analysis. This is generally used for organic compounds containing the element carbon, hydrogen, oxygen, and sometimes maybe even chlorine or sulfur. The point here, or you're familiar with combustion analysis, burning a compound in oxygen. By knowing the mass of the products and composition of the constituent element in the product, the original amount of the constituent can be determined. If you know the mass of the original elements in the compound, you can determine its empirical formula. It's assumed that all the original mass come from carbon to form carbon dioxide, and the original hydrogen forms carbon. So products for combustion products, H2O and CO2, carbon dioxide, which comes from what? Carbon and hydrogen. Once the masses of all the constituent elements are in the original compounds are being determined, the empirical formula can be determined. Probably maybe one example will illustrate, but here is the representation of what happened in combustion or what entails combustion. Generally, a sample is placed in a furnace. This is for combustion. Oxygen combined with or burn the unknown compound with known mass. By the way, you should know the mass. And then there is the CO2, H2O absorber. We can weigh the mass before and mass after to know the mass of the CO2 absorbed. Then from here, we can also weigh the mass before and mass after so that we determine the mass of CO2 produced. From here, we can determine the empirical formula for the compound, empirical formula for the compound. If we look at how the compound is obtained, right? You can have, let's say, for example, here combustion of 30.45 grams of a compound containing only carbon, hydrogen, and oxygen. There are three elements to produce 35.5 grams of 35.2 grams of CO2 and 14.42 grams of H2O. What is the empirical formula? This is a combustion. And by the way, the starting state word here is combustion. Make use of that so that you know what that means. So what we will do for that is, let's say if we looked at the calculation on how to find the empirical formula. Let's see, sure to set up so that we can look at how to determine the empirical formula. All right. So at the outset, we need to know the mass of carbon from CO2 from carbon dioxide. It's how we go about. We know the mass of CO2. It's going to be 35.1 grams of CO2. We use the molar mass of CO2, which is 44.01. 1 mole of CO2 times, for every 1 mole of CO2, there is 1 mole of carbon times the molar mass as a conversion factor grams of C. 1 mole of C. Let's understand what's going on here from the mass of, all right, from the mass of CO2, we need to find the mass of carbon. Okay, we need to find the mass of carbon by having this set up here. From the mass of CO2, we can find the mass of CO. So if you reconcile the units, this is grams of CO2, this will cancel out, this will cancel out, and what we end up with on our calculator, we shall have 9.6 grams of carbon. Now, mass of hydrogen from mass of H2O. We need to use H2O or mass of H2O, which is here, to find the mass of hydrogen. So mass of hydrogen is determined from the mass of H2O this way. So this is how you set up. Let me just put some space here. 14.42 grams of H2O. Using the molar mass as a conversion factor, 1 mole of H2O weighs 18.02 grams. So of H2O times this and that will cancel. 1 mole of H2O produce 2 moles of hydrogen. We have, for every 1 mole of H2O, 2 moles of hydrogen. That's what we have here, times the molar mass of H2O. 1 mole of H2O weighs 18.02 grams of H2O. And it turns out to be 1.62 grams of hydrogen. So we know the mass of hydrogen and the mass of carbon. We know the mass of hydrogen and we know the mass of carbon. So what we need to do is to figure out the mass of oxygen. Here, mass of what? Mass of oxygen is determined from subtract the mass of total mass of carbon and hydrogen from total mass of the compound. So we need to find the mass of oxygen by finding the mass of hydrogen combined from the mass of the compound. So how are we going to find that? This is going to be 30.45, which is this one, minus the combined mass, which is 1.62 plus 9.61. This is the mass of hydrogen. This is the mass of carbon, and all of them will be in grams. This will be in grams. This turns out to be 19.22. This is 22 grams of oxygen. So with all the masses of the elements we have, we can find the empirical formula. We say therefore, empirical formula for this compound is determined by this. So if I know this is going to be, let me just erase this right here, and I'll say the empirical formula. I just want to have enough space for that. This is our element. We have carbon, hydrogen, oxygen. So here is the mass. We have 9.61 grams, 1.62 grams, and 19.22 grams. So we know the mass of each one of them. We can find the number of moles. Let's see, number of moles given by 9.61 divided by 12.01, 1.62 divided by 1.01, 19.22 divided by 16.00. This is equals to 0.80. This is 1.60. This is 1.2. So if I have here, divide by smallest. You got to divide by the smallest number of moles, divide by the smallest number of moles. So the smallest number of moles here is 0.8. So this will be 0.80 over 0.80, which is equals to 1. Here is 1.60 divided by 0.80, which is equals to 2. 1.20 divided by 0.8 equals to 1.5. So if you look at the number of moles, all right, this right here, this right here, this right here, we need to make it a whole number. And remember the multiple for making a whole number, you need to multiply both all sides by 2. You want to make this a whole number by 2, by 2. So therefore, ratio is 2, 4. That is 2 times 2 is 4, and 1.5 times 2 is 3. So here will be 3. This is the mole ratio for our empirical formula for this compound. We say therefore empirical formula is C to H4 O3, and then you just express that. This is the empirical formula for this compound based on the mole ratio 2, 4, 3. For carbon, we have 2 carbons, we have 4 hydrogen and 3 oxygen, C243. C243. So that's how you use the combustion analysis to determine the empirical formula. So remember, in combustion analysis, pay attention to the elements. Use this mole ratio, the molar mass of carbon dioxide, molar mass of CO2 to determine that. Now, last part in chapter 3, organic compounds. Just gonna look at it briefly. I know you will cover inorganic chemistry 1, inorganic chemistry 2, so all goes on organic compounds. And what are organic compounds? Early chemists divided compounds into 2 types, organic and inorganic. Organic compounds were mainly those compounds derived from the living organism, whereas inorganic are those compounds which were derived from minerals. So compounds originating from the living things, right, were called organic compounds, originating from what the art inorganic. Organic compounds were easily decomposed and could not be synthesized. But nowadays, all right, nowadays we can synthesize organic compounds in the lab. Organic compounds can be made, can be synthesized from everything we can think of. Organic compounds are the major component of living things. That's true. They contain or they are composed of these 2 elements, carbon and hydrogen. And sometimes we can have oxygen, we can have nitrogen, or sulfur, even trace of other elements as well. The key element of organic chemistry is carbon. Why do we have, why carbon? Why not any other element on the periodic table? The answer to that is the only element on the periodic table is capable of self-linking, that it can form a long chain, all right? Well, propane gas, the octane gas and so forth. Octane for 8 carbon long chain, propane for 3 carbon chains. We're gonna look at that. So this is the only element on the periodic table which is capable of self-linking. It can form a long chain. Here is the simplest form of organic compound, methane. All right, CH4, it has only one carbon and 4 hydrogens. So this is what I was explaining about the ability of element carbon on the periodic table to form carbon atoms bond almost exclusively covalently forming or sharing of electron. There are few elements with which are organic, all right, such as the cyanide or hydrogen cyanide. I mean, cyanide ion. This is what I meant by the inorganic cyanide, polyatomic ion with a carbon. It falls under inorganic. When carbon bonds, it forms 4 covalent bonds sharing of electron, including single, double, and triple bond. Carbon is unique in that it can bond with itself and form limitless carbon chain. This is why we have organic chemistry. This is why we have vast amount of organic compounds because of the self-linkings, limitless chain. Self-linking, sometimes it can form a straight chain, some it can form a prime, some it can form a ring. Okay, it can form a ring. For example, propane for 3 carbon chain, prime for isobutane, or a ring, just to explain the bonding nature of organic compounds. Here, it can also form a double bond, triple bond, or double bond, triple bond, ethane, ethine, or even acetic as in acetic acid. Hydrocarbons are those compounds or organic compounds that have carbons. We can categorize organic compounds as hydrocarbon and functionalized hydrocarbons. You'll see the functional group later. Inorganic, organic compounds, or compounds can either be organic or this is where we are. There is hydrocarbon, which contain hydrogen and carbon. This is a class of compounds with only 2 elements, hydrogen and carbon. But here, functionalized, that means there is a functional group such as alcohol. We'll see that momentarily. Let's see hydrocarbon. These are compounds that contain 2 things, carbon and hydrogen. So know what hydrocarbons are. Hydrocarbon are composed of most common are such as oil, gasoline, liquid propane gas, and natural gas. Hydrocarbon contain only single bonds and are called alkenes. So you got to know the functional group here. Alkenes, all of them, they have single bonds. For example, in the previous one, while we call this propane A and E, there is all single bonds, no double bond. A and E, but E and E contain as double bond, but Y and E contains triple bond, so that you understand what the double functional group here in terms of alkanes. Alkanes, we call sometimes saturated alkanes ENE, we say that saturated. That means no they have single bonds, right there, single bonds. Whereas alkene with a double bond or alkyne, this is E, alkyne, triple bond, these are called unsaturated, unsaturated like that. We say unsaturated. So here, single bonds are alkanes, A and E. Those containing double bond or triple bond, that means alkenes and alkynes respectively, are unsaturated. You need to pay attention to how we use the suffix A and E, E and E, and Y and E. For the saturated, that means they will have single bonds. At least there must be a double bond and a triple bond for that. The base name for a number of hydrocarbons are listed here. All right. That means there is one carbon ethane for one carbon. So in other words, if it is just C with the two double bond, remember carbon form four bonds. So here, 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 we call this ethane. I want you to see how the ENE with the base name ethane. But if it is a double bond like that, remember carbon form four bonds, so it's going to be hydrogen, hydrogen here, hydrogen here, hydrogen here. We call this ethene. Ethene. But if it is double triple bond, see, there's only one hydrogen, there's only one hydrogen. This is ethyne, ethyne. How we use the word ethene for functional group. But if it is two carbon chain, we call this ethane, propane for three carbon chain, butane for four carbon chain, pentane, hexane, ethane, octane, nonane, and decane. And I use those in naming them. Now, what are the primary? This is a good question you expect on this section. What are the primary atoms found in alkanes? Carbon, hydrogen, and oxygen, carbon and oxygen, carbon and oxygen, carbon, hydrogen. Primary alkanes. We don't talk about oxygen in alkanes. The correct answer here is D, I mean D, carbon and hydrogen. Primarily, all right? Please learn the functional group for common one, structural propane for three carbon chain. This is what the three carbon chain for propane. Methane is only one, and butane, that means a straight chain, and pentane, it is a straight chain. Ethene, ethyne, and so forth. This is what you'll expect to see in the exam, all right? Functional group. Okay, it shows or is a group of functional group is a group of atoms which gives a molecule a characteristic property. It's a specific group of atoms, and it is part of the organic compound. All right, you're gonna have that C functional group. We are sometimes refer to as a family, a group of organic compounds with same functional group, same functional group. Alcohol, OH is a functional group. See this? OH is a functional group. Hydrocarbon, it can be a long chain, but the most important thing is OH is a functional group. We have other functional group, a double bond, triple bond. You need to know what the functional group for that. What is the molecular formula for propane? Propane, you need to learn how to name the hydrocarbons, CH 3 for propane. That means it is 3. You start building the molecule by starting with the backbone, the long chain. For propane, this is propane. And remember, carbon form 4 bonds. So there is hydrogen, there is hydrogen, there is hydrogen there is hydrogen here, there is hydrogen here, there is hydrogen here, there is hydrogen here, hydrogen here. If you count the number of hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, you write this as C3, C3, page 8. The correct answer for that is C. The correct answer is here. You know, without understanding how carbon form bond, it was mentioned, or I mentioned earlier on, that the form 4 covalent bond. It's include four dots. If you remember the dot symbol, we're gonna come back to that down the line. Carbon form 4 bonds. This is pentane for 5. You need to remember that. So if I look at this, I'll just use elimination method. This is 4 carbon chain. This is 6 carbon chain. This is 3 carbon chain. This is 7 carbon chain. Pentane for penta. So it's got to be 5. All right. Please complete chapter 3 Alex assignment before the next exam. All right.